All right. So the topic today, or for whenever you're watching this, is section 5.1 in Thomas, which is area with finite sums. But the real topic, as far as I'm concerned, because it's all about me, is how big is my yard? All right. Well, the backstory to this is I went to the local seed store to get some seed for my yard because it's a muddy mess now. And the old guy there, it's like kind of a one-man show. Well, how big is your yard? Well, I don't know. I said it's roughly, I don't know, maybe 75 square meters. Don't give me this square meters. I need it in fathoms. I'm like, fathoms? You really want me the dimensions? Is my great-grandfather was in the Royal Navy and blah, 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 something about fathoms and, Captain Cook and some stuff like this. All right, fine, fathoms. So I went back and I measured my yard in fathoms. And it turns out it's 1 fathom this way. It's a really short area there. It's 5 fathoms over here, and it's like 2 fathoms this way. All right, and a fathom is about 6 feet. No, I think a fathom is 6 feet. Well, it's a funny shaped yard, so I mean, how many square fathoms is this? Well, we're all clever mathematicians, and we know we can break this up into easier problems. So we break it up like this. Into so this is now 1 and this is now, what is that, 4, right? So the area equals, well, this area was 1 times 2 times 2 plus the area of this, which is 1/2 base times height, which is 1/2 times 2 times 4, which is 2 plus, what is that, 8, 4, equals 6 fathoms squared. All right, so the area is 6. And, but then my trusty assistant, Wally, my 2-year-old son, always likes to help with these kind of projects, and it always slows things down. In fact, I rarely get anything done once my assistant wakes up from his nap. And he's only 2, right? So the formula for a triangle is a little beyond him. And so I said, well, I guess we got to break this up into some easier ones, right? So into some rectangles he gets, right? But so we said, well, let's start with this light blue here, and we're going to just break this up into, well, maybe we can break it up into 2 rectangles, right? And then we have a little rectangle there. And then a little rectangle there. All right. Well, this is, and we could say this is a 1, and this is 1, and this is, well, how high would this be? Looks like maybe this is 1 to 5, and this is halfway, so that's 4. So this is like 3, maybe. So if we do it this way, it's 1 by 1. Now, admittedly, this is going to be too small, but let's say it's 1 times 1 plus 3 times 1 equals 1 plus 3 is 4, right? But we suspected that's too small. But I thought, oh, we could do better. Instead of making them smaller rectangles, let's make them bigger rectangles, Wally, because bigger is better. He's already accepted the fact that if sum is good, more is better. And so we're going to break this into 2 bigger rectangles. So now the area would be, and now we're only using rectangles here because triangles are beyond the scope of a 2-year-old. So this is 1 by 3 plus, let's see, 1 by 5. So 1 by 5, and that gives me 8, right? Which is too big, but it's too big, too small. And then Wally, right, knowing that if sum is good, more is better, let's make it into more rectangles, he said. I'm like, oh, yeah, maybe we can make more rectangles. Maybe that would actually work a little bit better. So what did we do? Let's do it in purple, right, my wife's favorite color. We said, let's make a rectangle here. And then we'll make another rectangle here, over like this. And then another rectangle here. And then the last rectangle here, right? Do you see it? So now I made 4 smaller rectangles. Let's see how we're doing. So this is 1, this is 3, so that means this is 2, that's still 3, this is 4, and this is 5 up here still. So now my purple area becomes 1 by, oh, now how small is the base of these things? Well, this is a total of 2 fathoms cut into 4 rectangles, so each one is a half. So this is a half by 1, so that's 1/2. And this is a half by 2, so that's 1. Plus a half by 3, which is 3/2. Plus a half by 4, which is 2. So that area equals 1/2 plus 3/2 is 2, 3, 5. Well, that's good. All right, so I'm getting closer. So by using more rectangles, I can actually get this thing to be a closer estimate. All right, and that's it. That's all we're doing today. Is we're taking some area. Whoop! Get out of there! Get out of there. Some area that we don't really know. And we're changing it into, or we're going to break it up into little rectangles, which are easy to calculate. Why? Why? Because the area of a rectangle, is simply base times height. Right? Now, why would we possibly do that when we can figure out, we know the area of a triangle, we know the area of a rectangle? Because math is all about dumbing problems down into easier problems. So that's what we're going to do next. And, oh yeah, I forgot, let's go to iTunes. No, we'll go back to this. We cleverly realized that if I drew some coordinates on this thing, if I made this the y coordinate, and I made this the x coordinate, my lawn equals 2x plus 1. Right? I can model my lawn with this function, 2x plus 1. Sure, at 0 it becomes, this is 0, 0 here. At 1, and then 2 times 2 plus 1 is 5. So yeah, my lawn fits this nice linear equation very nicely. Speaking of which, well, here's a nice linear equation. Y equals 2x plus 1. Here's what it looks like. And if I use these 2 rectangles here that are a little bit too small, I can see that my approximate area, the area of my rectangles, is 4, and the exact area is 6. Right? We already knew that. And if I make the rectangles too big, like that, right? Well, this one is 1 by 3, this one is 1 by 5, and so that means it's a total of 8 compared to my actual area of 6. Right? Now, this may still seem stupid, but all of a sudden, if I start to increase this, and I increase the number of rectangles to 4, right? I went from 2 to 4 rectangles. Notice that my area now, even though it's too big, it's only 1 off, whereas if I do that, it's only 1 too small, and if I do it, make the bigger rectangles, so I use the right end of my little rectangle to evaluate my function, so my rectangles are like this, versus using the left side, where I use the left side of my rectangle to get the height. All right? What happens if I increase the number of rectangles? 6 rectangles. Wow, now it's getting closer. Look at, because my error, which is really this little area here, is getting smaller and smaller and smaller, right? Because I'm getting better resolution the more rectangles I use. What happens if I do this? Oh, even smaller yet. Now I'm 5.5. I'm only half a unit away from the area of my lawn in fathoms by using 8 of these rectangles. What if I keep going? Yeah, 10 rectangles, even better. 12 rectangles, even better. 14, 16, 18. So now I get up to 24 rectangles, right? This is a pretty darn close approximation of the area under, the area under the curve, I was going to say. The area of my lawn by approximating it with a bunch of easy rectangles, right? Now, I have to do 24 rectangles, right? But a rectangle is still easier to do than a triangle. So 26, 28, and I go all the way up to 30. Or 38, I can go all the way to 40 here. And now I've got very little area. I've got 5.9 is my approximate area, all the way up to 6, which is my exact area, right? Very small error. Let's back off a little bit and see what happens if now these are too small because I use the left side, right, to get my height. I evaluate the function on the left side to get my height, evaluate the function on the left side to get this height of this rectangle. Right? If I do it on the right side, right, as we did before, this definitely makes the rectangle too big. Right? What happens if I use the midpoint? Let's try the midpoint. Ooh, now that's interesting. So if I use the midpoint approach, the left side of the rectangle is a little too big. The right side of the rectangle is a little too small. Right? But these exactly cancel each other out. So my approximate area is 6. My exact area is 6. Would that work for any function, right? No matter how many I make. If it's right with only 4 rectangles, it's going to be right for all the rest of them too. Okay? So again, why are we doing this? When I know I could break this up into a rectangle and a triangle, and it'd be much, much easier. Well, what if I didn't have something as nice? What if I had a parabola? Now, I don't know about you. I don't know the formula for the area of a parabola. So the best we can do is estimate it with rectangles. Let's start with the left side again. If I evaluate the height of my first rectangle by evaluating the function at the left side, f of 0 is 0. So I get 0 height there. Right? And then I split it in half, 2 rectangles, so the base is 1, the height is 0. 0. Again, split in half. The base is 1, the height is now, what is this? Y equals x squared, so that's 1. So my area that I approximate here is 1. When I know the exact, how do I know this? Well, we use calculus to do that. But I know the area should be 2.66. Right? I could use the right sum. Right? That means I'm evaluating the height of any given rectangle by using the right side of my rectangle. So f of 1 is 1. 1 times 1 is 1 for my little rectangle. And then the right side 2 goes all the way up to 4. 2 squared is 4. So the area of this is 4. This gives me 1. This gives me 4. So my approximate area is 5 compared to 2.6. Way too big. The midpoint. Okay. Well, the midpoint's pretty good here because I've got, it's too big here, too small here. So that kind of cancels out. Too big here, too small here. So that kind of cancels out too. And sure enough, my answer comes out pretty close. 2.5 versus 2.666. All right. But one of the questions is, in this particular case, what do I use as my height? My total base of my yard is 2 fathoms. I'm going to split it into 2 rectangles, which means I've got endpoints at 0 and 1, and 1 and 2. But if I use the midpoint to calculate my height, I've got to do a little bit more work. The midpoint is halfway between 0 and 1, which is a half. I evaluate a half, and that gives me a half squared as a quarter. All right, fine. And a quarter, so that's a quarter by 1, so that's a total of 0.25 for this guy. And then over here, the midpoint is halfway between 1 and 2. 1.5. 1.5 squared is 2.25, 2 1/4. And so I get 1/4 plus 2 1/4 is 2.5 compared to 2.6. All right. Now, something we'll touch on is, what if I used a trapezoid? Right? So I use my left corner and my right corners, and I do it like this. So now, I've really done a good job of approximating this. I have, I used both ends of my rectangle, and I know the area of a trapezoid is 1/2 base times height 1 and height 2, right? So height 1 plus height 2 is the average of my heights, and this gives me this. So I can use trapezoids to do this as well. All right. Now we'll see that if we do this, I know it's supposed to be 2.6, and I start to increase the number of rectangles. Even though I don't have a good formula. I do not have a formula, that's a geometry class formula for the area of a parabola. I can start to increase the number of rectangles I'm using. And boy, this starts to get pretty good. Right, I go all the way up to 40. So 2 divided by 40 right? There's, in this half unit section, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles for every half. So the base of each rectangle is 0.05, and the height of each rectangle is the height evaluated at the left side of the rectangle. Right? And of course that gives me an answer that's pretty darn close, within a tenth, but too small. Do it on the right side, pretty darn close, but a little bit too big. Use the midpoints, and it becomes very, very close. All right, so now we can approximate the area under our parabola by using a bunch of small rectangles. Now, we're going to develop some calculus tricks to do this much faster than adding up a bunch, but as far as the homework goes today, we're going to limit ourselves to this range, 2, maybe even 4 rectangles per function. But we might do left sum, we might do right sum, we might do midpoint. I don't think this section requires us to do any trapezoids, right? But trapezoid would be easy enough. And then Simpson, ooh, that comes really close, right? But we'll talk about Simpson's rule later. That's about all I really wanted to talk about. I'll show you a couple more examples. Here's a kind of a funny function here. 5 times the cubed root of x. Right, do that with left sums, that's pretty bad. Do it with right sums, not so bad. But again, we increase the number of rectangles. What gets better? Oh, so this begs the question. If 16 rectangles is better than 4, and 18 is better than 16, 26 is better than 18, right? What would be the ideal number of rectangles we could use? 100? 1,000? 1,000,000? Should we use an infinite number of rectangles? That would require the use of some limits, but I bet we can do it. Any other interesting ones? We got an asymptote here. No, this does not have an asymptote, but it's a bell curve looking thing, right? These can all be relatively easily calculated using these rectangles where we evaluate them at different points. Notice with this one, because it's generally downward sloping, that if we use the right side, right, it's actually too small. If we use the left side, it becomes too big. Whereas the first example we did, or the second one, the right side becomes too small, right? But depending on the function, the right side could give us too big, or the left side could give us too big. Right? So these are, I think, pretty straightforward. It's a little bit of a grind to evaluate these, but I didn't assign very many of them. But it's an extremely important exercise. This may seem like plug and chug, but again, it's a break from calculus. It's a little bit of geometry, a little bit of plug and chug, a little bit of tedium, but it's an extremely important concept that we're estimating the area of some strange shape with using a really simple shape or a bunch of really simple shapes, such as rectangles. I think that's all I've got for now, and if I think of anything more, I will put it up. Thanks for listening. Catch you guys later.